Hello and welcome. Again, I'm John Ball, the CTO and founder of Pat Inc. And today I want to talk about the thing that I find most exciting, Patom Theory. And it's quite a complex thing to talk about in 5 minutes, but it's something that I think in this long format stream, you'll be able to make sense of and understand how this differs from the processing model that we're all taught. So let's get into it. So Patom Theory, it's theoretical neuroscience, and it took 20 years of development to really get to the point where it was developed enough that we could say, well, let's see how this works with the cognitive sciences with some sort of AI application. Where it comes from is if you think about what is going on inside a brain, so whether it's a dog or a cat or a bird flying, the brain is very quick at controlling the muscle movements in order to navigate through the real world. So the sensory vision, in case of bats, it's it's the sound-based reflections coming off things that allow them to fly through night. The reality is that animals are very good at navigation by dealing with the world's sensory experiences, and then motion by using the muscles that we have, whichever ones they happen to be, because obviously flapping wings is quite a different activity to walking on hind legs. It's a different activity from crawling on all fours. But regardless of how the brain is connected to the rest of the body, it seems to be pretty good at movement and perception. So we'll keep going with then how do you develop that into a theory of brain function. So today's topics are going to be the process I took. So in 1983, I came up with the concept of a stadium model, a long time ago. What is it that allows the brain to work differently to a modern computer, a supercomputer, or I think even back then, Thinking Machines Corporation was building computers that had 64,000 processors each with 1K of memory or something. So very special purpose machines looking at how we can break through to AI. Then I'm going to talk about pattern atoms, how that then follows as an implementation for that stadium model, because the stadium model had some limitations. And then how does that lead into artificial general intelligence, so AI or intelligence, don't really like that word, but a system that operates like a brain that can then do general types of activities. So that's where we're headed today. So we start with the stadium model. And as a computer scientist at that point, I was trained in the fact that computer science focuses on efficient sorting algorithms so that we can do effective search. If you're accessing a database, you want to design the database properly so that you can get access to the information that you want from that database. That's an older concept that comes from using drums that became disks, using the old technology and trying to get access to a lot of information very quickly. Let's just explore that in a bit more detail. So here's a stadium. There's a lot of people there. And the question I would have for you is, if you want to find a particular person, how would you do it if you were a computer system? Well, the first technique that I think most people would adopt is you go around to every single person in that stadium and you ask them their name. And then once you know their name, you can put them into a particular seat so that you can say, if I have a name with this alphabetical sequence, you'll be in this. So you basically order everybody by alphabetical order. And if you then need to find a particular person by name, you can start with various search algorithms, maybe start in the middle and then you go left and right until you find the person that has the correct alphabetical name. That's great. The problem that you get is, what if you didn't just want a name? So in AI, what you'll often find out is you're trying to solve this particular problem and you want to bring something to bear on the problem that isn't alphabetical, like a bunch of factors. So you want to know, let's see, who has a red hat on today, is wearing yellow shoes, is under 23 years old but more than 15 years old, and whatever else. is holding a ticket that's for the B stamp. So that type of search requirement is very typical in the AI fields. And it's very hard to then build an index that caters for everything. It's basically an arbitrary index that would just give you nothing but constant indexing, based on name, based on age, based on shoe color, based on hat color. If you take your hat off, re-index everything, it would be a nightmare to administer. But we need to be able to do that. So the question is, how would you do it with a stadium model? What you would do is you'd broadcast out to everybody in the stadium, and you'd say who has a hat on, who's got yellow shoes, who's 18 years old. If you meet that criteria, come to the middle of the stadium, and you just watch for a couple of minutes. And if people walk out to the middle, maybe 5 people walk out and they've all got their hats on and they've all got the yellow shoes, then you can do some narrowing down. But you want to very quickly shortlist your requirements, and then you want to shortlist the group that meets all of those requirements, because potentially you've got duplicates. We call that ambiguity in language, but in linguistics. But fundamentally, there might be more than one. Fundamentally, there might be none. And if you think of it, the most inefficient way of search, particularly for these general things, is to go through everybody. If it's 50,000 people in the audience, okay, well, you've got to do 50,000 database record pulls and then go and look at the particular details, and then you shelve that and you come up with the next one. It's very inefficient if nobody meets your criteria. And what's worse is if nobody meets your criteria, you think, oh, what if I just change it a little bit? And then you have to search everybody again. And I'll change it a little bit, search everyone again. So the most efficient way of doing this is the stadium model implementation. And you're probably thinking, okay, well, that's kind of cute, but does it really work? Maybe, maybe not. So let's just keep going here with the next step. Let me just find my presentation so that we're going through correctly. Okay, so imagine now we go from that stadium model to this arbitrary room. This room could go on for 100 miles in one direction, 100 miles in another direction, all with these seats. And the broadcast method would allow us to push out to all of those people who has the information I'm looking for. They could press a green button on their desk, for example, and come up with the answer. So what that looks like is an agent-based system. And I was computer science trained, and the whole concept of writing a program is that I've got my agency, I can decide what it is I want to do, and I can write a program to do it. And AI at that time was looking for, how do we get the intelligence of that program, because the program then can act based on what I've told it to do. How do we get it to learn that automatically? And that's where you really hit the problem of computational models. If you want to put intelligence into thousands and thousands of machines, how would you ever train it to do that? And I can't think of how you do it. But that's the Pandemonium Model. That's an old model from Oliver Selfridge back in 1959. But those types of models are the opposite of what Patom Theory finally became, which is the opposite of that. Rather than having any intelligence, we use a pattern matching technique to rapidly identify all of the cases that match amongst an arbitrarily large search space. So you could have hundreds of trillions of possible desks here, and potentially just get one broadcast and response to get the answer very efficiently. And that runs on modern computers as well, if you simply set it up correctly. So that's the concept of the stadium model. Obviously, there's some problems. How would you make that work? But that was the concept of it. Let's just get rid of that, because that's a bit annoying. Okay, so we want to find the right seat. So this Pandemonium model. So Oliver Selfridge posited this idea for understanding our senses. Simply have a whole bunch of these little demons, these little machines that would be monitoring for a particular type of shape. And if you match that shape, they raise their hand, and then all of the ones at one level, all of these little agents at one level can pass the details to the next level, and then agents at that level can combine them and try and work out what's going on. They can then pass it to a higher level. So it was this hierarchical model of agents. And okay, that reasonable approach. My question remains, how would you make these agents learn? And if you can't make them learn, you haven't done anything other than say, well, I've got a brain, isn't that great? Now we'll just put inside of our heads hundreds and hundreds of other brains, and they all solve the problem. So you're not solving anything, you're simply pushing the problem down to the next level of resolution. I think if you went back to, what is it, 1600s, there was this concept of a homunculus where you've got the Descartes. I think he had this little man sitting inside your brain that was monitoring everything, the soul probably, and it's just watching the information coming in from your vision, and then it's making all of the decisions. So you're simply taking the problem that you want to solve and giving it to some sort of magical being to solve it for you. And inside that little magical being is obviously another magical being, and you then get an infinite number of those. So the comparison to that processing model, which has some problems, is the pattern matching model. And if you could learn a pattern and then match it and then use it, as in it's part of a bigger model, well, then that solves your problem. That's the beginning of Patom Theory, and we'll get into that in a lot more detail in a moment. Yeah, so before we go on to the patterns, let's just have a look at what we have on the internet. So I said that the idea of indexing is a big part of computer science, and you can see here with the sorting algorithm that in computer science, this is Wikipedia, a sorting algorithm puts elements into an order. Efficient sorting is important for optimizing the efficiency of other algorithms, such as search and merge algorithms that require input data to be sorted lists. So I'm just reinforcing the fact that it's not hard to find what we expect, but you then have this challenge of needing an infinitely large index to index everything in advance of knowing what it is you really need, which makes your system very inflexible. And if you think of how people operate, we are able to learn, and as we're learning, we constantly don't seem to have our brain shut down for 30 minutes or something while we re-index stuff. There's a very immediate result as we're learning new things. So let's now just evaluate this Pandemonium architecture that I talked about. You can see that it's very old. Oliver Selfridge is talking about it in 1959, and Selfridge and Marvin Minsky, who was a guy I collaborated with as a kid, 20 something years old. We had some dialogues, and his main point to me was, don't think this stuff's easy, and I think that's worth passing on. NLE is not easy, AI is not easy, but one of the reasons it's not easy is because we just don't have the right scientific framework that explains it, and that's what Patom Theory has been focused on ever since that point. So Pandemonium architecture, you can see we have a model here which has layers in it, but what's kind of cool these days is that people have then done a bit more work, and you can actually see it in action. So here's somebody that's gone to the trouble. What's the website called? cdn.cinhour.com, and here's their feature daemons at the bottom, cognitive daemons. So you can see the feature daemons are looking for particular lines, the cognitive daemons are looking for letters, and then you've got a decision daemon that sits over the top. So each of these are little agents that are looking for something and then producing a result. So in use, you can see all these little feature daemons are asleep. We hit the capital A, the big capital A, and some of these guys wake up and they start pandemonium. They start jumping up and down. Hey, I've got something. And then the higher level demons here, the A is very happy. That it's the right answer. X is a little bit happy. So you've got different levels of enthusiasm at the cognitive level, and then the decision one chooses the A, which is the correct answer for this one. So you can see as we go through different letters, here's an H. This guy's pretty happy because there's the left and right side of the H, and here's the middle bar of the H. These guys are all asleep, and the decision demon gets the right one. What if you have some messy thing like this, looks like an A to me? What do we get? So we're getting the A is a little bit interested, the X is a little bit interested. So yeah, it's got an X in it, it's got an A in it. It's guessing, oh, look at that, A and X. It's finally guessed. Yeah, it's sort of rotating around. So my point is, well, this is what Pandemonium theory does. And okay, it's a theory, but Patom theory goes to the next level, which is you have to get rid of those intelligent machines that are doing some process, because firstly, who knows how you'd automate writing computer programs like this, and then secondly, how is this going to generalize to various other things? Like at the pinnacle of human capabilities, the pinnacle obviously would be language, because with language you're able to speak to somebody else in your tribe and say, hey, don't go to the waterhole this morning because the lions are waiting there, and you've just saved all of the lives of those particular animals, of your friends, in fact. And so it's a survival benefit to have good communications, and the more accurate your communications can be, the more survivability you're going to have, particularly if you're taking on bigger, stronger, more dangerous animals. And the same type of thing would apply to other forms of food gathering, and so forth. So there's our Pandemonium model. If we compare that computer processing model to what we're looking for with AI, with cognitive science, you can see here's just an article at random. Search on what is computer processing and you get stuff like this. And you can see that people like to say the CPU is a type of electronic brain for a computer system, and it's not a good analogy. If you went back a couple of hundred years, people would be modeling the brain as a bunch of gears. I think Charles Babbage and Ada Lovelace were talking about that particular model. And then after that, it was some sort of steam-powered machine, with pressure that's actually producing brain capabilities, and then it became like a telephone switch, because you get inputs to a neuron and then it switches and off you go. We like using the latest technology in order to model what the brain does. And so we're stuck at the moment with the computer processing model as the brain, and it's just a terrible analogy, because that's not how brains work. It's not what they look like they're doing, and you can't come up with some method that says this part of our brain's writing programs, or all of our brain writes programs, but we can't see how it works. There's just this fundamental problem which Patom theory explains. So let's go back to pattern atoms. And this is something which I think the long form video is helpful for, because if you think of, there we go, I'm big again. If you think about it, Patom theory is complicated, and if you write it down, you can say in Patom theory, all the brain does is store, match, and use hierarchical bidirectional link set patterns, where link sets are sets and lists. And great, you can write that out. Nobody knows what it means, and you've got not a whole lot more engagement in it. So it's not a processing model, it's pattern matching. And then people would ask the question, what's processing, what's pattern matching? And you're kind of stuck continuing to argue it. So let's just do this sequentially so that I can make the point. Obviously, there's no database in your brain. And probably the most complicated task that you would want to do as a machine is to track what's going on in a meeting. Who's speaking, what did they say, who else is in the meeting, who's left the meeting, so who heard the stuff while they were in the meeting and didn't hear things when they were out of the meeting. All of that stuff that human brains do extremely well. And if you try and do that with a database, it's pretty hard. So let's go through what I've just said. What's a patom? A patom is a short form for pattern atom. Why is that important? Well, if you point at something in the brain, it's connected to a whole bunch of other things. And the question would be, well, what is that connection? So my argument is, when you're pointing at that thing in the brain, it's an atom of a pattern. It's representing something that might have forward projections to something, which also goes back to that particular atom, and vice versa. So a brain is this hierarchical model where you've got vision and auditory and other sensory information connecting to some sort of pattern atom, and then they project forward to the use of that particular pattern atom. We'll become a little bit less obtuse. There's a word. We'll make it a bit clearer in the future. All the brain does is store, match, and use patterns. Patterns are one of two things. They're snapshots, as it says on the bottom there, or lists. So in order to deal with motion, you have to have a list of patterns. So if you've got a snapshot, think of that as a still image. And then if you have a sequence of them, think of that as some sort of timeline. There's a few areas in our experience where lists are important, like the passage of time, like the sequence that events take place in the real world. And then there's sets where you're recognizing that particular objects can be modeled with a whole bunch of different things. So we need to take into account the fact that the objects in the world are composed of perhaps a whole set of other objects. That comes back to pattern matching theory, in fact. And the hierarchical and bidirectional nature is when you talk about the letter A, you can recognize in your head what that would look like. You can also recognize the words that you would be using the letter A in. So there's some sort of use of the A in words, and then there's the recognition of the letter A in a wide variety of ways. So here's one of my old slides. Brains don't process information. I'm really trying to hit the point that pattern matching is different from processing. If you're a computer scientist, you're taught that the process is you take your variables in memory, you then bring them out of the memory and you put them into registers, and then you select something from the CPU or arithmetic logic unit, and you then process a couple of those registers, change the one of the registers with your new result, and then potentially you store back the new result into your memory location, and then you can potentially persist that out to disk and so forth. So that's the processing model, and there's this program that's controlling it, the sequence of instructions that allow the whole system to operate to solve a particular problem. And again, how do you write that program automatically to deal with everything that we experience from running? So let's think about a brain. When you're running, and this is where the sets and lists gets stressed, you're controlling your body. So you're balancing your body with perhaps only one point of contact or no points of contact on the ground at a point in time. You're moving your arms, and so that means you've got signals going from your brain down to your muscles in order to move your arms correctly. You've got signals that are controlling your legs, controlling your head, controlling what you look at as you're running. All of that output activity to control muscles is also being supported by input through your vision, through your sensory, through your skin as you're detecting wind, through your hearing as you're hearing things. All of that system has to work together as a single unit. And the idea is that if you're storing not the full sequence, not every muscle sequence, but a summary of those, then you're sort of going up this hierarchy. So you've got, if I want to run forward, here's the basic program, if you like. This is the sequence of muscle contractions in order to move forward, and muscle relaxations. You don't want to be fighting against yourself as you move. So sitting up in your brain, you're seeing this stream of pattern coming, and then your brain is sifting through that and finding more particular combinations of those patterns and more particular combinations of those patterns, and then somehow it's going to integrate that with all of the other sensory experiences to recognize objects and to control your motion in the particular event that you're in. So that's the goal. So that's very different, as I've just described it, to a processing model where somebody would write a program, they'd define their databases or data structures, and then manipulate things so that you can control your robot that's using these muscles. And incidentally, today, in 2006, we were looking for a good project to run, and we chose language. And the reason we chose language is because it's more effective at proving this type of brain theory than other types of approaches. So whereas the brain theory is clear with language, if you put a sentence out and ask, that happens to be a question, you get a result back from the system that knows the answer that's rendered correctly in the language that you put the question in, you can say, well, the brain model is working. If you want to build a robot that is emulating what a person does, and you've got no muscles, you've got no vision systems except for compressed MPEG feeds and all of the things that make our technology good for the purpose that it's designed for, well, you're going to be waiting a long time to produce the right type of system. So that's the goal here of Patom theory, to be able to do take what a brain does and use it in the real world. Get that out of the way. It's probably a bit annoying. If you could even see that. Okay, so, well, what's a pattern? The brain has access to a lot of patterns. And if you're writing a database for this, you've got a big task. So there's a symbol. It's a 1. But it also looks a bit like the letter L. If I wrote hello and I use those 2 instead of the L's, I use 2 1s, I'd still recognize it. And if I had hello and the last O was the number 0, I'd still recognize that. And you know other associations. It's an integer, a character, a symbol, noun, and then your pronunciation of 1, if you recognize that as the symbol 1, you need to have that too, because you can build patterns based on that. So the point of laboring the point at this point, that 1 has a lot of information that is available to a brain, because nobody that's watching this had to stop the video feed and think about, well, how else can I recognize this? How can I really recognize this sound? You know you can. So let's put that basis, that principle now into use in language. So we've got the cat sat on the mat as a sample sentence that we want to recognize. And you can see we're showing here that there's a letter T, there's a letter H, there's a letter E. It's possible to misinterpret that, any of these letters, but still recognize the word the based on the sequence. So you can see here we're recognizing the word the, which then has its own, in this hierarchy, it has its own features and pattern elements that we can then use to solve the larger problem of, oh, the cat is a type of reference phrase. It means cat, and we've already identified a particular cat in context, which is why I'm saying the cat rather than a cat. And then we hit the word sat. And so we're able to handle language by using this hierarchical model. And then here's one of the Selfridge examples, which helps illustrate this point. See, we've got the cat here, T-H-E-C-A-T. But the H in the is in fact the same character as the A in cat. And we effortlessly recognize that because both of those symbols mean A or H. You can recognize that. It sort of looks like the top's been cut off of the A, but you can recognize that with your visual perception. But it's not visual perception that says it's cat necessarily. It could be a sequence in some in your reading center of, and that happens to be in your vision center as well. We read from the thing called mailbox, which is left side anyway. Not worry about the detail. But the cat is something that you can recognize as a sequence, even though there's what you could call noise introduced into the system. And if you're not going to take a hierarchical approach to how brains work, you've got a real problem, because that H and that A is exactly the same character. You cannot resolve it without going up another level and saying, oh, the makes sense, te does not make sense in that sentence. Or, it might make sense in another language, so you have to be careful of that too. There's nothing that you can anticipate in advance that says this is the arbitrary convention that we're using for the signs in our linguistics or semiotics model. Okay, let's not dwell on this to death. So what else are we doing in interacting with the real world? What is it that our brain, the human brain, is doing, like when we're in a meeting? So here's a problem. We're having a real world meeting, and what a person is keeping track of is the names of attendees. Obviously, if you've got 1,000 attendees, you're not going to know the 1,000 names, but you'll know the people on the stage, for example. You're recognizing what they look like, how they move, if they've got particular mannerisms. You're recognizing who said what, which is like a transcript. You're recognizing where they are on the map, because you can have a Zoom call and you can have somebody in New York and someone in San Francisco, and you can keep track of the fact that's where those people are, so that when they make some comment, you're able to say, oh, he's talking about the game, he's in New York, he's talking about the Yankees. Oh, yeah. So all of those things have to be represented somehow. And for you computer scientists, how are you going to write a database to represent that in real time, where you're bringing in video, you're bringing in auditory, you've got your transcriptions, you're keeping track of who's saying what? It's a challenging problem, which without Patom theory, I can't think of an answer for. And let's see, coffee meetings. So there's a bunch of things that come out of meetings, such as, well, what kind of meeting is it? You know, you can be meeting at a coffee shop and there's a couple of people, and you've sort of got this concept of frames, because you know what two people at a coffee shop, what that meeting looks like and what the sequence of events are. If you're in a big town hall meeting, you know what those sequences of events are. If you're at a fast food restaurant, there's a different sequence of events. At a fast food restaurant, for example, and this is where the frame theories come into play, and I'm starting to digress, but I'll get back to the topic in a moment. When you go to a fast food restaurant, you order and then you get your food. When you go to a very fine dining restaurant, you order your food, you eat it, and then you pay. And those types of minor distinctions about the sequence are simply pattern sequences that we can automate through systems based on pattern theory. If you wanted to come up with a nice program model that says, here's the sequence of events that takes place, you're going to be constantly tinkering with the model, because you'll have one program for one type of restaurant, a different program for another, a different type for a coffee shop, and potentially you're going to have an infinite number of these that you're programming up and then reproducing to program up a different sequence. That's the problem. I'm not saying it's insurmountable with modern technology. I'm just saying it's a hard one to solve, because I don't see many systems around that can do all of these components. In fact, I don't see any that can do all of these components, like a human. So, patterns can be learned, but can you learn programs? When I've read modern papers about, we've written, you know, we've got this great breakthrough in brain science. We've worked out that the synapses are doing some sort of processing technique. So we've got not only the, you know, trillions of synapses in the brain, but each one of them's like a little computer doing an agent type function. Okay, I don't like that model. It's a slightly worse model to, I have this neuron, and the neuron's intelligently acting, you know, if it's in your occipital lobe, it's intelligently acting to recognize vision. Like, how would that ever come to pass, that you would have that? And why does that part of your brain look identical to other parts of your brain that do radically different things? How would the neurons know I'm a vision neuron versus I'm an auditory neuron versus I'm some other type of neuron? It doesn't make any sense. So the alternative to the programming model is this composition model. If you look at the history of linguistics, people talked about language being a compositional system, and the constituents of particular sentences are identified with all of their components. That's how the system that we'll be showing you in other long form videos, that's how that system works. But if you were to link people in their location, so if you had an atom that was for a particular person, and another atom for another particular person, I can choose some at random. John Ball, Alan Turing, and someone else are in a meeting. So if you know that I'm John Ball, you know who Alan Turing is, even though he's not alive anymore. You could imagine us being in a meeting by simply adding us to this fictitious meeting event, and then we can say things, and I can be talking about Patom Theory, as I would likely be doing. Alan Turing would be talking about perhaps his imitation game, or the contributions he made to building computers back in the 30s and 40s, and, you know, helping the Allies win World War II. We could have an interesting discussion about those types of things. But all we're doing is we're accessing the atoms and we're dropping the atoms in. If you know a particular room, you can drop that as your background. If there's a meeting with people in different locations in different rooms, and you know those rooms, you can have the information about those rooms associated into that particular event. So all we're trying to do is associate other things into an event and track it that way. So that's the concept of how we can compose our recognition of the world very easily, because all of those things are human capabilities, and we want to replicate those in our machines in the future so that we're getting the same strength that people are bringing to bear on the machine, so that it can then share its insights with us as we would share with other people. What's this saying? Pattern matching relies on meaning of resource, not something blank. How do I get rid of that? Let's get right. The pattern matching relies on the meaning of resource, not something predefined, not a database. So what we're talking about there is, if you were to say, I like red, you're talking about the color red, because that's what red means. Potentially you could be talking about I like to read. It's a different spelling and different pronunciation. Or I have read, in which case you're talking about reading in the past. But we don't need to spell everything out because the meaning comes from the word itself. So you don't need to say I like the color red when it's good enough to say I like red. Right, so the meaning comes from that. And the reason this all works is because we take a view that the brain isn't just that thing in your head, it's actually the integrated nervous system. So the neurons in your eye are part of your brain. The neurons in your skin are part of your brain. It's just that they're extending out through the use of the nervous system. When we look at the picture there, you can see that there's the human brain. It's got the green temporal lobe, which is where language is coming in through the auditory patterns from your ear. It's finally getting into the cortex in the temporal lobe. You then get the recognition of words themselves, and at the back of that little green area is what's known as Wernicke's area. People with damage to Wernicke's area can still speak, but what they say is maybe grammatically correct, but meaningless gobbledygook all the same, because they're not able to get the meaning of what they want to say out through our voice. In the front of the brain, in the frontal lobe, the gold piece, there's a section called Broca's region, and if that's damaged, an area that's right near the motor cortex that controls the mouth and larynx and so forth. If you get damage there, you can't speak. People are at pains to produce words because presumably the patterns that make up the speech are impacted because the speech that they've learned it's been destroyed, so they can't just do this incredibly rapid speech that comes from language. And there's different localized areas in brains. They're all different, of course, but there's different localized brains that do different types of magic. At the back of the brain, you see the purple bit. That's the occipital lobe where vision comes in, and there's a little 1 millimeter square region that's known as V5. That's our ability to recognize motion. And if you lose both sides of your brain in that region, you can no longer see motion. You can basically just see like snapshots of vision. The question is how you would produce that if you don't have a model like Patom Theory. The pink bit at the top is the sensory motor, the sensory input, and other features of the parietal lobe. And the tiny little piece at the bottom is the cerebellum that helps us with very fine motor control. So all of this brain works together with our senses, and it's a remarkable machine. But it's not to say that it's remarkable in the same way that language is remarkable, because dogs and cats have very similar capabilities, not the language part, but very similar capabilities in terms of recognizing their environment, recognizing people and friends, and controlling motion. Now here's another way of looking at it. Here's the brain topology, and this is what I just talked about, but let's summarize it again. You start with your senses. Each sense is individual, and inside of those senses we can recognize firstly the basic patterns, and then the brain specializes and finds smaller types of patterns within that sense that can then provide, for example, motion and vision, or particular objects in vision. That then projects onto a region that eventually deals with multisensory patterns. So it's pulling all of the patterns together in order to produce an object. So you can imagine if you bake a cake, the smell of that cake, in order to connect, it has to be connected to the visual part of cake, and then of course the motion that you're using to prepare the cake. All of these things fit together. And it's not the reverse, but in order to move, you've got your multisensory patterns that have to be worked with in order to decide what you want to do. And then those patterns can be, for example, to move, to walk. You can have those patterns that are a set of muscular patterns that allow you to, for example, stand up and start walking forwards. And you would imagine that those types of patterns are at a very high level, quite simple, and at a very low level, simple sequences. And by controlling those sequences correctly, we then have motion. So it's quite a different approach to the problem of AI than you'll often see, because this is what brains actually do. And the main function of a brain in this case is to recognize sensory input and determine appropriate muscular outputs. And that's got to be a useful survival skill, no matter how you look at it. The other thing to focus on here is that the patterns that we're talking about here are bidirectional. So a multisensory pattern is able to go back through the individual patterns of individual senses to get at the original source. And that source is the sense itself that we've experienced. Now, it's not like a movie, because the brain's not generating movies. It's simply recognizing things. Get my little head back in so you're not missing me while I'm talking. Okay, so we're learning these hierarchical patterns. So we're going from sensory to multisensory. And you would think that you would just go from senses straight to all the other senses. That's not how the architecture works. We go from sense to multi-sense in a discrete area, which is very interesting. And the patterns are bidirectional. So when people who are computer experts talk about this, you would imagine that you're taking some sort of visual scene or multi-sensory scene and compressing it into a nice little database object that you can pass around. To take away the complexity that would be required there, firstly, how would you encode this information in the first place? And then secondly, how would some other brain area decode it? That would be a very complex thing to evolve. As opposed to, I've recognized something, I'm telling you I've recognized that thing, and then the thing that has recognized it can go back and get historical information as to what it looks like, smells like, tastes like, if it's dangerous, and so forth. And that's the bidirectional nature. And then the fact that these are linked patterns. In the stadium model, we talked about broadcasting out a name and then waiting for somebody to respond to say, hey, that's me. In the case, the reason you have linked patterns is that when you learn something, you make a physical connection between the elements that compose it and how it's being used in an event. So you meet somebody, you can then store the fact that they have a name, which is auditory, and that they have a particular look about them, which is visual. And so you link back to the vision and the auditory to connect that together. You can also connect your emotions and so forth, which advertising people love to manipulate. But that's the concept. We're storing in our visual brain the visual memories that we've got, which is quite a different concept to compressing and encoding and sending through these data packets and unpacking them and using them, which we do with computers for obvious reasons. It works really well in a computer where you're writing the programs around it. And then what are these linked patterns? They're sets and lists only. We don't want to have very complex environments to deal with. So you don't want to have a database structure. You want to be able to say, if I follow this path back to my sensory information, I'm accessing a baseball. And if you're going forward from the baseball, the thing at the other end knows it's a baseball because it's got an association to the name that we've given it in English, baseball. And so there's my slide explaining it with a bit more detail about the components of this hierarchical bidirectional system. Okay, let's go into a bit more processing detail. So we're not talking about data anymore. We're talking about patterns. So here's a concept of intersection. So one of the challenges that you'll have is if you've got a possible word that has multiple meanings, for example, you need to be able to say, well, is this consistent with what else I know? And so I created this concept of link set intersection, where a pattern atom is a connection to all these other areas. But if you've got a few patterns that connect to different areas, you want to be able to intersect those three patterns and find something that's consistent with the other input that you're looking at. So think of it as I've got three sets, and then I intersect it with the current context, and I get one result. Sometimes you get multiples because some things are ambiguous, but let's say a lot of the time you're resolving things to only one pattern, and that's probably the reason our conversations are as effective as they are. We're not constantly saying, what do you mean by that word and this word? Because in context, these things are not ambiguous. In fact, you can inject ambiguity into a conversation as a joke, because usually you have something outrageous and then the thing that you actually mean, and people get both. So we find that amusing. But down here you can see, you can see that we're seeing two types of A's. That's because we've converted it from my original image into this format, and it's converted a bunch of different letters into the underpinning representation, little a, capital A. But even if you imagine that we've got a whole bunch of different fonts, there's Gothic fonts and very formal fonts, you finish up with capital A's and lowercase a's. I'll have to do another video sometime where I have the original source, because it's a bit cuter than this. But you can see that the computer's quite happy to convert these things into their meaning, which is capital A, little a, using its particular font rather than the suite of fonts that I'd provided. Have to use a graphic next time. So in practice, here's an example of pattern theory. We're recognizing symbols, which we saw the H and the A can be ambiguous in the cat. But here we've got the cat sat on the mat. We're recognizing symbols. Whether you recognize those accurately or not, we then recognize words. And whether you recognize those accurately or not, you then recognize phrases. And the phrases, you can see in the word the, we have embedded the word he. But you don't notice that because the word the is recognized as part of the phrase the cat. The word at is inside cat. But again, you don't recognize at because cat is being recognized. So these longer sequences can, if they're good matches, can then extinguish the lower level matches in terms of what you're actively perceiving. And then each of these can have a bunch of features and their own life of their own in terms of how that pattern works. So the word the operates whether or not we know how to spell it, even if we've only got the auditory sound. And that leads to my joke here. And you've got some letters and numbers. You've got, let's see, any one, and then there's 41, and then 0S. And if you think about what does that communications mean, what did I intend it to mean, it's anyone for tennis. Anyone for tennis, which is an auditory pattern. The 10, the 1, 0, maybe you wouldn't pick that up. And you wouldn't pick up 10S to be tennis, but after you've seen it, you often will just see that instantly. So let's wrap up with a quick talk about artificial general intelligence. So artificial intelligence is the human endeavor to replicate brains on machine. And it's been around since the 50s, been around a lot longer than that. We've wanted to have robots working with us for a lot longer than that, but it became a formal science in 1956 with that naming. And Patom Theory is something that's come out of the cognitive science analysis to say, well, this is what brains do. How can we build machines based on what the brain's doing to progress science? So I'm very excited about Patom Theory because we've seen it in action in linguistics, and we see the potential for future machines that are going to improve the lives of people by taking away a lot of the drudgery and the inefficiencies and just leave us with powerful tools that make our lives better. What will we talk about next time? Next time we're going to be talking about the application of Patom Theory with a modern linguistic theory, role and reference grammar. Role and reference grammar came from the amazing discovery that I made. It's been around longer than Patom Theory has. Role and reference grammar came from Robert D. Van Bellen Jr.'s work with Bill Foley back in the early 1980s, and they came up with a system and a book that explains how linguistics works if you start with the diverse languages of the world rather than the alternative, which is we'll start with this formal theory and we'll see if we can apply that to the world's languages. The insights are amazing. And it works perfectly with Patom Theory because Patom Theory says, what is a brain doing in order to perceive and manipulate the world? These guys started with what does linguistics do, And they then worked out a model that applies to all of the world's languages, that's taking into account the semiotics connection, the syntax to semantics, and back the linking algorithm, and how context works in line with that system. So it's a very interesting application of linguistics that we can also show you working on computers. So that's pretty exciting. So I think we'll wrap it up there. Thanks very much for joining me again today. I hope you're enjoying these long form versions, and feel free to refer back to these after you've seen a detailed long form explanation, so that you can tie the engineering work that I'm showing you in a detailed analysis with the scientific work, which is why we're doing it that way rather than some other way. So thanks again for joining me. See you again soon. This is John Ball signing off.